Okay, so in section 10.3 in physics, what we have been talking about is we've been talking about torque and forces and how the torque and the force affects the motion of something or keeps it static, one of the two. So in section 10.4, what they're talking about there is they're talking about explosions and collisions. And one of the things they say, and again, I'll upload the PowerPoint for you, but one of the things they say is that when we try and analyze forces and motion in an explosion or in a collision, that can be very hard to do because there's so many forces, there's so much torque, there's just so much going on at any given point during that explosion or during that collision that it's very, very hard to analyze. And so back a little while ago, we talked a little bit about this, and we said that one of the things that people like accident reconstructionists, those types of people, what they actually do is they look at what was the momentum of the objects before the crash or the collision occurred, and then what was the momentum and the direction of the objects afterwards. And from that, they really can tell a lot about what was going on during that explosion or during that collision. So that's what we're going to be looking at in section 10.4. We're going to be looking at explosions and collisions. Sorry, I have puppy dog eyes looking at me. We're going to be looking at explosions and collisions. So, and we're going to be looking at it at least at the beginning of this section, in terms of momentum. So if we think back, don't lick the leg of the chair, no. If we think back to talking about momentum, momentum was represented by little p, not a big P. Big P is power, little p is momentum. And momentum is mass times velocity. And there is no unit for momentum, it's just kilograms times meters per second. And the other thing we talked about in terms of momentum was we talked about there is a conservation of momentum. The momentum of the objects in total before the collision have to equal the momentum of the objects after the collision. And remember, we're not talking about 10 minutes after the collision. We're talking about right after, like milliseconds after the collision. So the law of conservation of momentum said, if you take the momentum, which is mass times velocity, if you take the momentum of object 1 and you add it to the momentum of object 2 before the collision, it has to equal the momentum of the first object plus the momentum of the second object after the collision. Those have to be equal. And again, remember when we talk about before and after, we're not talking about 10 minutes before and 10 minutes after. We're talking about like the moment before the collision, the moment before the explosion, and the moment right after. All right? So there's no new formulas here. There's nothing new. What we're going to do is we're going to apply the idea of resolving things into components, into X and Y components. We're going to take that concept and we're going to move it over into the idea of momentum and the law of conservation of momentum. I'm really hot, just a second. And so we're going to look at the model problem at the bottom of page 505. And if you are looking at that with me, if you have your textbooks open, I know I'm dreaming, but I'm saying, if you had your textbooks open, you would see that this example is about 4 or 5 pages long. Good news is the reason why it's that long is because they actually give us 2 methods for solving that. The first method involves us drawing it using a protractor, drawing it to scale, measuring the angles. Again, not really very accurate. especially if you are not a very accurate drawer, which we all know I'm not, so, and neither are a lot of you. So the other method is much, much, much more math-based and involves us using the component method. So we're going to read through the problem, do what we always do, make our list of information, and then we're going to break this apart into its pieces. So, a billiard ball. So we're going to put MB for billiard ball. A billiard ball has a mass of 0.155 kilograms. All right. It's rolling directly away from you at a velocity of 3.5 meters per second. So I'm going to put VB1 because it's the initial velocity of the billiard ball. What they do, excuse me, what they do in the textbook is rather than put a little 1 down here, they put a little prime up here, a little apostrophe. It's called a prime in math. They put that up there. I don't care which way you do it. I just find it easier to put it down there. It doesn't make any difference. It's 3.5 meters per second. And it says it's rolling away from you. So let's say I'm here, okay? I'm gonna need that space for math. Let's put it up in that corner. Let's say I'm here, the ball is rolling away from me, so it's going that way, okay? Doesn't matter really what way you put it, but I'm gonna put it that way. It's rolling away from me at 3.5 meters per second. Now, it collides with a stationary golf ball that has a mass of 0.052 kilograms. So mass of the golf ball is 0.052 kilograms, and the initial velocity of the golf ball is nothing because it's stationary. Now, the billiard ball hits the golf ball, and the billiard ball rolls off at an angle 15 degrees clockwise from its original direction. So if this is its original direction, when it hits the golf ball, let's say the golf ball's right here, when it hits the golf ball, it goes off at an angle 15 degrees clockwise, so 15 degrees clockwise from its original path, all right? The question that they ask is, oh, and now it has a velocity of 3.1 meters per second. So the second velocity of the billiard ball is now, you'd think I could remember that long, but I can't. It's now 3.1 meters per second. So it's slowed a little bit because, you know, it came into contact with something else. It wants to know what is the final velocity, what is the velocity right after the collision of the golf ball. Now remember, they're asking for velocity, which is a vector, which means not only do you need a magnitude, you need a direction, all right? If you only give me a magnitude, I can't give you full points. So we are going to look at x values and we're going to look at y values. We are going to look at the two of those. So we're going to look at we're going to look at the y direction and we're going to look at the x direction, okay? So let's do the x direction first just because I happen to have it on the board. So for the x direction, mass of the billiard ball times velocity of the billiard ball plus mass of the golf ball times velocity of the golf ball, and here we're talking about before the collision, is equal to mass of the billiard ball times velocity of the billiard ball plus mass of the golf ball times velocity of the golf ball, and we're talking now about after the collision. So before and after, they have to be equal. This is going to be way easier than you think. So the mass of the billiard ball is 0.155. In the x direction, well, at at the beginning, this billiard ball is going totally in the Y direction. It's not moving left or right in my drawing. It's going directly in the Y direction. So its initial velocity in the X direction is actually 0. Plus mass of the golf ball is 0.052. And the initial velocity of the golf ball is 0 because it wasn't moving. It wasn't moving in the X direction and it wasn't moving in the Y direction. That is equal to the mass, and I'm going to put the equal to down here because I need space over there for this one. So I'm going to put the second half of this just below it. So the mass of the billiard ball is 0.155. Now, here's the tricky part. The velocity of the billiard ball, but in the X direction. So if I make myself a little Cartesian plane here, right where the golf ball was, right where the billiard ball starts moving off in another direction, I can make a right angle triangle. Again, you always make your right angle triangle to your x-axis, not to your y. So that would mean that this is 3.1 meters per second because they said it's going off at 3.1 meters per second after it collides. This is 15 degrees, which means this is 90 minus 15, which is 75. So that is 75 degrees. That's a really bad 5, but that's 75 degrees. And here's my x and here's my y. So if I want to know what is the x portion of this, that is the adjacent over the hypotenuse. So that is cos of 75 is x over 3.1. So that means that my velocity is 3.1 times cos of 75. Okay? Plus mass of the golf ball, which is 0.052, times the velocity of the golf ball. Now I have no information about the final velocity of the golf ball, so I'm just going to have to leave it as an unknown. So this side of the equal sign is just 0, and this is 0.155 times 3.1 times cos of 75 plus 0.052 times the velocity of the golf ball. So we can isolate that, right? We can bring this over to this side and divide everything by 0.052. Now I'm going to cheat and I'm going to look in the textbook for the answer because I'm lazy like that. And the y, they say, no, we're doing the x, sorry. The x component, they say, is negative 2.3916. We're not going to round that off. We're not going to worry about significant figures because that's not our answer. That's just the x component. We're going to go through exactly the same process, but for the y component. Okay, so I'm going to write this down here. VG, the x component, is negative 2.3916 because I'm likely going to have to erase this. So same thing, we're going to do before for the billiard ball, before for the golf ball, after for the billiard ball, plus after for the golf ball for the y component. So mass of the billiard ball is 0.155. Velocity of the billiard ball in the y direction before it collides. Well, before it collides, all of its motion is in the y direction, and it said that its initial velocity was 3.5. So it's just 3.5. No need to do any trig or anything there because all of it is in that direction. Plus mass of the golf ball, which is 0.052, times velocity of the golf ball. Now remember, this is before the collision, so it's stationary, so it's nothing. I'm going to put the other half underneath because of space issues. So underneath, I'm going to have, after the collision, the mass of the billiard ball is 0.155. Now I need the y component of the final velocity. So the y component's up here. It is the opposite over the hypotenuse, which means it's sine. So it's exactly the same process. It's just sine, right? And that's the y component. So we're going to do 3.1 times sine of 75. So that is the mass times the velocity. Plus, now we have to do the golf ball. The golf ball is 0.052. And we do not know the y component of the golf ball. That's really what we want to figure out. So this is 0, we know that. So just be careful with this. Oh, sorry, there it is. Just be careful with this. This is 0.155 times 3.5 is equal to 0.155 times 3.1 times sine of 75 plus 0.052 VGY. When you bring this over here, you have to subtract it. A lot of people divide it, but that is not following algebra rules, right? So 0.155 times 3.5 is actually 0.5425, and I would subtract 0.155 times 3.1 times sine of 75, right? I would subtract all of that, and that would equal 0.052 VGY. That's an equals. So after I go through that whole process, so I take this, I subtract this, and then I divide by 0.052, I get that the y component to the golf ball, and again I'm cheating, is 1.507. So I have no space. So VGY is 1.507. I need that, but I have to erase this. I'm putting it over there. All right, so now that I have that all figured out, I need not the components of the velocity, but I want just the velocity of the golf ball after this collision. So if I know the x component and I know the y component, I can use Pythagorean theorem and I can figure that out. I can do negative 2.3916 squared plus 1.507 squared is equal to my velocity of the golf ball squared. Please, 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 do not round this off to say like negative 2.4 and 1.5. If you do that, if you round it off too much during your calculation, it's amazing how much it throws your answer off. There's a couple of people who do that quite often. You're trying to take shortcuts, you're trying to do it quicker, easier, whatever, and I understand that, but it really throws your answer off. So leave it out at least 3 or 4 decimal places to be sure you're being accurate. So when we do that, the velocity of the golf ball turns out to be 2.8 meters per second. But that really is just its speed. Velocity also means that you have to have a direction. Now, I want you to think about what signs this is. My x is negative, my y is positive. My x is negative, my y is positive. So the golf ball's going to be going off in this direction in some way, all right? Because my x was negative 2.3916 and my y was 1.507. So if I want to figure out what this is, I'm going to use tan. I'm going to go tan of theta is 1.507 over negative 2.3916, although I would not worry about the negative because that may throw your answer off. I really want an answer between 0 and 90 degrees. I want what's called the principal angle, so I really wouldn't bother with the negative. I would just use the positive of both of them. And if I do that, if I do 1.507 and I divide it by 2.3916 and I do tan of that, I get 32 degrees. Theta is 32 degrees. So this is 32 degrees. Now, how am I going to put that? How am I going to explain that it's 32 degrees, but it's 32 degrees over there? How do I say that? I say it this way, okay? This is the x-axis, right? This is the x-axis. And if I start at the x-axis, I'm going 32 degrees in the counterclockwise direction. So when I give my answer, the velocity of the golf ball is 2.8 meters per second, 32 degrees counterclockwise. Actually, you don't have to write out that whole word. Let's use the abbreviation CCW, counterclockwise from x-axis. Because you really can't say left, right, up, down, north, south, east, west, because it isn't. It's just we put an XY axis, meaning that up was away from me and across. So you really can't say that it's north or south or east or west or whatever. All you can really say is that it's 32 degrees counterclockwise from our x-axis, and that's all you can say about it. A lot of people want to tell me northeast, southwest, but nowhere in the question were we talking about northeast, southwest. All right, so that's it. We're only doing one example. Takes long enough to record one example. So we're just doing one example. There'll be a few questions for you to try. I think it's 35, 36, 37, but just check in Google Classroom. Just check what I said, but I'm pretty sure that's what is in my notes. My notes are way over there. I'm not going to look at them. And be working on your assignment, please. Don't forget that you do have that assignment due. But I wanted to get through some of these examples because I think there's one or two questions that actually apply. So I wanted to get through these. Looking forward, just let me look. Looking forward, there are, I don't know. 1, 2, there's only 2, no, I lied, there's 3. There are 3 other model problems. If we find that we're not getting through the work and there are questions that apply to it, all we'll do is we'll just extend the due date on that assignment. Not a big deal. I'm not going to expect you to hand something in that has something we haven't even covered it on it yet. But we already have covered most of it, so you can be working on it. Don't go, well, we haven't covered everything yet, so I'm not starting it. That's not smart. Don't do that. All right? Be doing what you can do. I think there's only 2 or 3 questions at the end at most that we haven't covered yet. So be working on that. Again, per video, I'm probably going to do 1 example, and that'll be it because the examples take so long. Mr. Brownlee was talking in a meeting about how we should do chunks and just do 1 example at a time. And I'm like, I do, but it's still like 30 minutes. I'm sorry. So that's it for today. We'll see you on Monday. Bye.